All right, up to this point, we've been looking at how the electrons in atoms can arrange themselves. Specifically, we've gotten into how we have a set of valence electrons in an atom based on how they arrange themselves and which electrons end up farthest out in the electron cloud. We talked a little bit about forming ions, so charged atoms by gaining or losing electrons, which ultimately make them more stable. In short, that comes from, is it easier to lose electrons to back up to the previous noble gases electron configuration, or is it easier to gain electrons to get to the next noble gases electron configuration? The octet rule tells us that 8 valence electrons is a usually pretty stable set of valence electrons. So it's kind of a magic number for making the electron cloud stable in that farthest out energy level. So if we can get something to 8 valence electrons, that tends to be an electron configuration of a noble gas, and therefore we've made things a little bit happier. Whether we lose or gain electrons doesn't make a huge difference, other than we want to pick the path of least resistance for that atom. We don't want to make it go through more work than it should have to get an octet. And to note, some things are better off getting a duet than an octet. So things like hydrogen and lithium are more okay with just getting 2 valence electrons rather than a total of 8. That way, we don't have to worry about trying to force more electrons on some, even though we can get it to a stable noble gas configuration with helium. Okay, so we're going to be taking that a step further to see how this process happens, because up until this point, when we say something has given electrons or taken electrons, we kind of don't care about what happens to the electrons after that. So lithium loses an electron and it just is flung off into the void of space, and then we don't care about it anymore. Or we say that chlorine is going to pick up an electron, but from where? It just kind of gets one somehow, So we have to look at what happens to those electrons and how we can make kind of the best situation out of different atoms needing electrons or getting rid of electrons. What we're going to do is basically make substances made of multiple elements, typically a metal and a nonmetal, by getting them both to benefit from a give and take of electrons. Okay, if something is willing to give up electrons and something is looking to take electrons, then maybe that's a match made in heaven. And both things can end up being kind of happier and more stable by one being the giver and one being the taker. For instance, let's look at sodium and chlorine. Sodium is a metal and chlorine is a nonmetal. And again, we're going to see this trend kind of happen between usually a combination of a metal and a nonmetal. So sodium, to stabilize as an ion, is going to end up losing some valence electrons, as a lot of metals do. Sodium starts with 1 valence electron. So it would be a lot easier to lose that 1 valence electron, if you want to be grammatically correct, rather than trying to gain 7 valence electrons or something like that. Now, I say it reaches 0 valence electrons, but don't forget that does still abide by the octet rule, since 0 valence electrons means we go back to the previous energy level, which should be full with the previous noble gases electron configuration. All right. If sodium loses 1 valence electron, that should give it a charge of +1. All right. Since each electron is negatively charged, so 0 minus -1 from that 1 electron it lost would equal a +1 charge. Now, don't forget that we have this weird kind of thing that in chemistry we kind of write this backwards. We write it 1 plus instead of +1. Okay? And the reason for that is kind of historically, as far as I've been able to figure out, we used to write multiple charges like a +2 charge, not as a 2 with a plus or something, but just plus plus. So if you wanted to do 3 positive charges, it'd be plus plus plus, and so on and so on. So if you wanted to summarize that and say, well, I have 2 positive charges, you would say 2 plus. And it kind of stuck. So we write those kind of backwards of each other. So where is that electron going to go if sodium loses it? Well, maybe it needs something to give it to. Let's look at chlorine. Chlorine starts with 7 valence electrons. So to get to an octet, it would be easiest to gain 1 valence electron. I'm going to be grammatically correct and cross that out. So overall, we start with a neutral atom. We add 1 negatively charged electron, and so it should end up with a -1 charge. I'm going to write that with the 1 first and then the minus afterwards. So that would get it to 8 valence electrons. Okay, so these have a common interest. Sodium can give its 1 valence electron to chlorine, and they'll both end up happy. Now, it might be a little bit easier to show this than to write it. So let's go down here. We're going to do Lewis dot diagrams to show how sodium and chlorine start and end, and how we end up making an attraction between these. We end up making a new substance out of these ions. So sodium's got 1 valence electron right here. Chlorine has its original 7. 1, 2, 3, 4, 5, 6, 7. All right. And I'm going to draw an arrow to show sodium giving that valence electron over to chlorine. Just like that. Okay. What we're left with is sodium with no valence electrons. And again, it technically has an octet, but a lot of times in this case, to kind of emphasize the fact that we've lost an electron, we don't go and give this 8 valence electrons. We just kind of assume that it does because it has lost those valence electrons. So instead we keep it like this, but we do want to show it's charged. So I'm going to write a little 1 plus up in the top right here. All right, our chlorine now has its original 7. 1, 2, 3, 4, 5, 6, 7, along with an 8th electron that it has picked up from sodium. So it now has a total of 8. It's got an octet. It's now more stable as well. All right, and by picking up 1 extra electron, it now has a negative charge, which we write as a 1 minus charge. All right, now a lot of times you will see +1 charges and -1 charges written without the ones. It's implied. Otherwise, we wouldn't write the positive or the negative in the first place. So a lot of times you'll see it like this: Na with a little plus and Cl with a negative like this. It's not technically wrong to write the 1 plus or the 1 minus to have the 1 explicitly in there, but it's not necessary. So a lot of times you'll see it kind of removed to make it a little more simple, make it a little more clean. Okay, so this over here, this set of ions is now a lot more stable from that give and take of electrons, and they now have an attraction. Positive charges attract negative charges. So these ions are going to attract to each other and stick to each other. So not only do they make each other more stable, they also now are going to stick to each other. This attraction is called an ionic bond. So we've got a positive ion, a cation. We've got a negative ion, we call an anion. And that attraction between them is an ionic bond. All right, and altogether they make an ionic compound. A compound being something made of more than one element. Okay, specifically held together by ionic bonds, so we call it an ionic compound. To name an ionic compound, we put the cation name first, followed by the anion. But we do a little trick. We chop the end off of the anion and make it IDE instead. Okay, so if this was a compound made of sodium as its cation and chlorine as its anion, we chop this end off So instead of chlorine, it's going to be chloride. All right. So in total, the name is going to be sodium chloride. Let's take that off here. Rewrite this. Sodium chloride. I should have made that line bigger. All right. So this way we can name the compound and show that it is something different than just sodium and chlorine together as two separate elements. We've made a new substance that has new properties, okay, and therefore it needs a new name to identify it. So this one we would call sodium chloride. The formula, right here, the chemical formula, is basically just saying how many NAs and Cl's does it take to make this ionic compound more stable. So for instance, again, we're putting the cation first, Na, and we had one of these, so we're going to put a little one down here. We had a Cl, put the anion second. All right, and we had one of those. Okay, and our formula looks like that. Okay, now, again, like the charge, you don't really need the one. The one is implied. So I'm going to erase those. And this is more commonly how you'll see the formula for this compound. So sodium chloride has a formula of NaCl. Right? So these are both ways we can identify the ionic compound, either by the name, sodium chloride, or by the formula, NaCl. Okay, so that's an example of how we can make an ionic compound. Through a give and take of electrons, where everything is mutually benefiting, we end up with an attraction between the ions that we make. We call that attraction an ionic bond, because it's bonding together ions. And then we make a compound by putting those ions together and making a new substance that has its own properties. Let's look at another example. In this case, we've still got chlorine, but we are using magnesium instead. Okay, so based on the last problem, we know that chlorine starts with 7 valence electrons. And if you needed to figure that out, don't forget, you just look at the periodic table, you figure out what column it's in. If it's in 1 or 2, it's got 1 valence electron or 2 valence electrons. You skip past columns 3 through 12, and starting up at 13 again, you start dropping the 1. So 13 becomes 3, 14 becomes 4, 15 becomes 5, and so on and so on. So chlorine is column 17, so it's going to have 7 valence electrons. So we should expect it to gain 1 electron to reach an octet to make it an anion with a charge of -1. I'm going to write it backwards, 1 negative. Okay, well, what about magnesium? Magnesium is in the second column of the periodic table. So it has 2 valence electrons to start with. All right, so it would still be easier for magnesium to lose electrons rather than to gain electrons. But instead of losing just 1 valence electron, we're going to lose 2 in order to back up to the previous noble gases electron configuration. So magnesium is going to lose 2 valence electrons, ends up with an octet by backing up. Okay, so we're going to end up with a cation, a positive charge. Since we lost 2 negatively charged electrons, 0 minus -2 equals +2. So this should have a +2 charge. I'm going to write that as a 2 plus. All right. So this is what we should expect. But this doesn't come out as nice and neat just looking at the numbers here. Like chlorine's looking to gain an electron and magnesium's giving up some electrons, but magnesium wants to give up 2 electrons, and chlorine really only wants to take 1. We can't force chlorine to take both. That would give it 9 valence electrons, which is not more stable. We need 8 valence electrons, that magic number. So maybe we need more than 1 chlorine atom. Let's try and draw it out. Magnesium starts with its 2 valence electrons. 1, 2. Oops. Do it like this. So it's going to come out a little bit cleaner. Put 1 there, 1 here. Each chlorine starts with 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. All right? So magnesium could give up one of its valence electrons over to chlorine on the right side here, and that would get this chlorine to an octet, which would make it happy. But magnesium's still got an electron to lose, so it's not quite there yet. This chlorine also isn't happy either. Okay, well, maybe if I gave this other electron to a different chlorine, then this chlorine would get to 8 valence electrons. It's stable, it's happy, and magnesium has lost its 2 valence electrons that it started with. It's good to go too. All right. So what we would be left with is magnesium with no valence electrons other than the 8 that we kind of have in the energy level underneath what we were looking at, with a positive 2 charge. Again, we show that with a 2 plus up in the top right. Each chlorine has a negative 1 charge, but the 1 is implied, so I can do a little negative sign, and our chlorine had 1, 2, 3, 4, 5, 6, 7. Let me put those in the same place, get it consistent. 7, 8. Each chlorine went from having 7 valence electrons to picking up an extra one from the magnesium, leaving it with 8, giving it an octet. So these guys are following the octet rule. Okay, so this all together is our ionic compound. And just like with sodium chloride before it, everything winds up stable. So everything is mutually benefiting. We have positive and negative charges that are attracting each other. And a good sign that you've made a good, stable, strong ionic compound is that all your charges cancel. We don't want any positives or negatives left over. So magnesium has a charge of positive 2 that needs to cancel with negative 2 charge. So in this case, we've got it from one ion with a negative 1 charge and another ion with a negative 1 charge. Okay? This also goes to show that you don't need to give your electrons to the same thing. You can split them up a little bit. Give one electron to one thing and one electron to another. Okay? So if we were to name this ionic compound, again, we start with the cation first, which in this case, the positive thing is magnesium. Starting with magnesium. That part doesn't change. What does change is the second element. So chlorine, again, loses its ending. So instead of being chlorine, it becomes chloride. Let's rewrite this. Chloride. The formula then is just counting up the number of cations and anions you need to make this whole thing stable. Well, we had magnesium, and we only needed one of those. We just had one of these guys. Okay, so again, I could put a little 1 down there, but it's implied. I'm going to leave it out. Okay, then I have 2 chlorines. So I'm going to put a Cl for chlorine. Instead of writing it twice, I can say, hey, I've got 2 of them. So I'm going to put a little 2 down here. Call that a subscript. All right. So this little 2 means that there are 2 chlorine anions here to make this thing happy. All right. So by name, I can call this ionic compound magnesium chloride, or by formula, I can call it MgCl2. Either way works. Okay, let's look at one more example. All right, this one I'm going to leave up to you to figure out because it follows kind of the same trend as the one from before. But this time, I'm not giving you kind of the before and after template. So in this example, we kind of could see that we needed 2 chlorine atoms because I already had them written there. In this one, we don't have that written out already. So you may need more aluminum atoms or more bromine atoms than just one of each. So my advice to you here is don't forget that you can have multiple aluminum atoms or multiple bromine atoms to make this thing happy. Okay? And don't forget to make sure the charges cancel. Right? Think of having kind of like a pool of aluminum and bromine atoms you're smashing together to make this thing work. So we're not limited to just one of each or one of this and 2 of this. Just make sure you can make everything happy. Get everything to an octet. Okay, if something wants to lose so many electrons, make sure it loses all of them. Okay, if something wants to gain electrons, make sure it gains all of them. Don't leave any leftovers. Make sure you either get down to 0 valence electrons, aka 8 in the previous row, or gets to 8 valence electrons by gaining. Okay, so other than that, I'm going to leave that to you to try and figure out. Let's look at this last one here, because this is going to be a toughie. So we'll do this one together. Okay, so we're going to make ionic bonds between magnesium and nitrogen. Well, magnesium is familiar from the last one. Since magnesium starts with 2 valence electrons, we would expect it to lose those 2 valence electrons, meaning it's going to be left with a charge of positive 2. We write it as 2 plus. Not so bad so far. If we go and find, that's a leftover, has an ion. We go find nitrogen on the periodic table. Nitrogen is in column 15, meaning it starts with 5 valence electrons. So it is going to need to gain 3 valence electrons to get an octet. And it's going to leave it with a charge of, well, start at neutral plus 3 negatively charged electrons. That leaves us with a negative 3 charge. And we write that as 3 minus. Okay, so let's try and make this happy. Let's try and make this happen. So I'm going to start with my magnesium, Mg, and it's got its 2 valence electrons. I'm just going to put one there and one there. Just kind of spread them out a little bit. I've got a nitrogen over here. It's got 1, 2, 3, 4, 5 valence electrons. Okay, well, my magnesium is looking to lose both these electrons, and nitrogen's looking to gain 3. So maybe I could give one away there and give another away right here. Okay, so that would make, fix that one a little bit, that would make my magnesium happy. It's lost its 2 electrons. It did what it was trying to do. But my nitrogen is still now just up to 7 valence electrons, which is a little short. I'm still missing one. So if this nitrogen is looking to gain 3 electrons total, I'm going to need something else to give it another electron. Well, what's giving me electrons in this case? Magnesium. Magnesium is giving up its electrons. So I need another magnesium ion. So let's just kind of put up here for now. Give it 2 valence electrons. All right, so I can give 1 valence electron here. That will get my nitrogen up to 8, 2 from this magnesium, 1 from this magnesium. So this nitrogen is now stable and happy. But my magnesium is not. It's still got this 1 valence electron it hasn't given up. So I need something to take it from this magnesium. What do I have that can take electrons? That is nitrogen. So let's make another nitrogen over here. All right, it's got 5 valence electrons to start. 1, 2, 3, 4, 5. I give up this magnesium's other electron. Bring it over here. That means this magnesium has lost its 2 electrons. So it is happy, it is stable. But this nitrogen is now left at 6 valence electrons. So we just cannot find the end to this. But we might be very close. What I have left is nitrogen with 6 valence electrons. I need just 2 more valence electrons to make this nitrogen happy. Well, what can give me 2 valence electrons? What else but another magnesium? Mg starts with 2 valence electrons. Give 1 there and 1 there. This magnesium is able to give up both its valence electrons, so it's happy, it's stable, and this nitrogen has now gained a total of 3 valence electrons, meaning it is happy and stable. So everything is happy now. It took a lot, okay, and it's not very clean, but it all worked out pretty well. So let's draw the result on the right side here. What I wind up with is 3 magnesiums, right, and 2 nitrogens, The nitrogens have their original 5 valence electrons, plus 3 that they were able to get from these other magnesium ions as they gave up those electrons. Right? So my magnesium should have no valence electrons left showing. Right? Now, in order to make sure this isn't a cluttered mess, we're going to put these guys in brackets. This is also just kind of a common thing you see for ions. So to show that these are stable ions, we're going to put these guys in brackets. Bracket there, bracket there, bracket here. And each of these magnesium ions, by losing their 2 valence electrons, should be left with a positive 2 charge. Positive 2, positive 2, positive 2. Whereas these nitrogen atoms have gained 3 electrons each, meaning they each have a charge of negative 3. So 3 minus, 3 minus. So this is my ionic compound. It should be noted that you don't really have to make your ions in this exact kind of arrangement. You could kind of have them on 2 levels, kind of, 1 row and 2 row. You could have it something like over here. But it kind of helps to kind of clean stuff up so you can make sure everything got the electrons they needed or got rid of the electrons they needed to get rid of, and to make sure your charges are all canceling. I've got positive 2, positive 2, positive 2. That's a total of positive 6 charge from my cations. 6 plus. And I've got a negative 3 and a negative 3. That's negative 6, 6 minus. For my anions, what I'm left with is 0 charge. All my charges canceled, which is a good sign of a happy, stable ionic compound. My name for this ionic compound starts with a cation, which is magnesium. That part stays the same, magnesium. And the cation, nitrogen, the anion, nitrogen, loses its ending and becomes IDE. So I would chop the end off. Now, it can be a little bit weird to figure out where exactly to chop the name off. Typically, it comes after the first hard consonant, like nitr, and then we chop it off from there. So if you're stuck between, is it going to be nitrogide or nitride or nitrogenide? Usually after the first kind of hard consonant noise, that's where we chop it off there. So this is going to become nitride. All right. So let's clean that up. Nitride. So this compound is called magnesium nitride. The formula also starts with a cation, Mg. We needed 3 of them to get this formula to work. So down in the little subscript, I'm going to write a little 3 here, say that we had to use 3 of them. All right, and to cancel out that charge and to get everything happy, we needed 2 nitrogen ions, 2 nitride ions. So I'm going to put a little subscript 2 down here to say that I needed 2 of them. Okay, and that shows my ratio of cations to anions to make this compound stable and happy. All right, so I could call this compound magnesium nitride, or I could call it Mg3N2. Either way, we're talking about this compound here held together by the ionic bonds between the magnesium cations and the nitrogen anions.